Okay, welcome to the linear algebra class, and let us consider this is theorem 3.7. Okay, we proved the theorem 3.7, and as I said, its meaning is that when you have, say, two matrices A and B, then their product cannot increase the number, the rank. Okay, so or if you consider the composite of two linear mappings, the rank cannot be increased by the composition of two linear mappings. So that is the meaning of theorem 3.7. We proved it and we considered a few examples, right? And then we consider the augmented matrix. Okay, so what is the augmented matrix? If I have two matrices A and B, say A is m by n and B is m by p matrix, then when I say the augmented matrix, which is denoted by this, or in some textbook or paper that you may see a notation without this vertical line between A and B, and then some people use the square bracket to imply the augmented matrix, but the parenthesis can be any parenthesis can be used. So the meaning is that the contents the A and B are merged to define a larger matrix. So if A is an m by n matrix and B is m by p matrix, both have m rows but different number of columns, then what you do is you just write down the entries in A first, and then you write down the entries in B just next to it, so that the number of columns is increased to m plus p. So you get m by m plus p matrix, okay, by appending the entries of A and B. So that's the augmented matrix. Now, okay, now let A be an invertible n by m matrix. Okay, so A is an invertible. That's the assumption here. So if A is an n by n invertible matrix, and then let me construct an augmented matrix C by appending A and n by n identity matrix. Since A is invertible, if I multiply A, the since A is invertible, we have the inverse of A exists such that A inverse times A will be the identity matrix, right? Now, please remember that when I multiply two matrices A and B, and if B consists of, say, B1, B2, up to BP columns, then when A is multiplied to B, it is multiplied to each column. So A times the B1 will form the first column of the product, and A times the B2 will form the second column of this product, and eventually A times the B sub P will define the pth column of this product. Okay, so if you remember this, then when I multiply A inverse matrix to this augmented matrix C, this A inverse will be multiplied to each column in the augmented matrix C. So eventually that is the same as, so that the result will be the huge augmented matrix, and the first n columns are obtained by multiplying this A inverse to A matrix, and the next n columns will be obtained by multiplying A inverse to the identity matrix. because this C is constructed in that way. Now, A inverse times A will produce the identity matrix, and A inverse times the identity matrix will produce A inverse, right? So, what is the point here? So, let me highlight this. So, we assume that A is an invertible matrix, okay? And given this invertible matrix A, I constructed this augmented matrix C with A and identity matrix. Given this augmented matrix C, if I pre-multiply A inverse to C, you have n by 2n matrix. First n columns will be the columns of the identity matrix, and then next n columns will be the inverse of A matrix. Okay. Now, previously we learned that any invertible matrix can be written as a product of elementary matrices. And that means even this A inverse can be written as a product of many elementary matrices. Okay. So A inverse can be written by the product of these. So the equation number one implies that if I multiply the inverse matrix of A to this augmented matrix, you get this one. Now, what is the meaning of this? What is the meaning? Okay, first of all, when I say A inverse is the product of these elementary matrices, okay? So what is so and what does this what do they do? E1 up to EP. These are elementary matrices which transform A to identity matrix. Okay? So, given A, we know that if A is invertible, then we can transform A to the identity matrix by performing some row operations. Right? By performing elementary row operations, we can always transform A to the identity matrix. Right? So, so if you do that, so given this matrix, multiplication by E1 up to EP. Okay, that means, so here, multiplication by this, and this E1 up to EP, when multiplied to A, you get the identity matrix. So that means, so here, EP up to E1, those are elementary matrices which transforms A to the identity matrix, right? Then, so that means, so multiplication by this, this is equivalent to saying that row operations on A to transform that A matrix to the identity matrix. So if you perform some elementary row operations on A to change this A to the identity matrix, that is equivalent to multiplying these elementary matrices. Okay, that's what you do above here. Okay, so if you do that, if you, right, now what is the next part? The multiplication by this elementary matrix to the identity matrix will become the inverse of A. So given A matrix, given A, I know how to transform A to the identity matrix, right? I can find certain row operations, okay? So if I do those row operations on the identity matrix, so if I perform those operations on the identity matrix, your identity matrix will become the inverse of A. That's the meaning of this expression. Okay, multiplication by E1 up to EP to this augmented matrix will generate this matrix. Okay, so given A, you need to find some elementary row operations which will transform A to the identity matrix, right? We can do that. We can identify those. Now, if you perform those, the same elementary row operations on the identity matrix, then your identity matrix will become the inverse of A matrix. That is the meaning of this expression. Okay? Okay? So you can read these two slides for the proof of what I told you. So let me explain this one more time. Okay. Okay, given A, if it is invertible, if it is invertible, we can find elementary row operations which transforms A into the identity matrix, right? So that is the meaning of this expression, okay? Then, okay, if you perform the same row operations on the identity matrix, then identity becomes the inverse of A. That is the meaning of EP up to E1 multiplied to the identity will become the inverse of A. Okay. So here, so this, so this product multiplied to oops, A will become the identity matrix. So if you multiply the same elementary matrices to the identity matrix becomes the inverse. Okay, so from this identity, that means I can find some elementary row operations corresponding to E1 up to EP, which transforms A into the identity matrix. For those elementary matrices, so that means if I perform the same elementary row operations on the identity matrix, your identity matrix becomes the inverse of A matrix. Okay, that is the meaning of this statement. Okay, so when I say this statement, okay, its meaning is what I just told you. Okay, now, so that is the case when A is an invertible matrix. But what if A is not invertible? Then we cannot find such elementary matrices E1 up to EP which transforms A into the identity matrix, right? And also, what does that mean? I mean, what is the meaning of non-invertible matrix? Then what will be the rank of such matrix? Please remember that A is invertible. That is equivalent to saying, okay, so let me write down here. So given n by m matrix, it is invertible. And we know that if A is invertible, then the rank of A is n, and vice versa. If the rank of A is n, A must be invertible, right? So if A is not invertible, that means we can say that the rank of A is not n. Of course, that means rank of A is less than n. Okay. Now, the in that case, rank of A is not n, and rank then means the rank. How did I find the rank of a matrix given A, when I perform elementary row operations, eventually your A will become, or elementary column operations as well. Then when the rank is R, your A will become this matrix, will be transformed to a matrix of this shape. If the rank of A is R, A can be transformed to such matrix, right? And when I say elementary row operations, okay, so if or elementary column operations, that means this can be obtained from A by performing some elementary row operations. That means I can multiply the corresponding elementary matrices from the left. Or if I perform the elementary column operation, so that means I can multiply some corresponding elementary matrices from the, say, from the right. So this will be this. Now, multiplication by elementary matrices do not alter the rank. Okay. Anyway, so that means if the rank is less than n, so that your matrix is not invertible, then by performing some elementary row operations, you will definitely see some zero row, right? If your matrix is not invertible. If your matrix is not invertible, so that your rank is R and that is strictly less than n, in that case, you will see a row of zeros if your matrix is not invertible, right? So these two slides explain that situation. So if your matrix is not invertible, then your rank of the matrix is not n. That means the rows and columns are linearly dependent, especially rows are linearly dependent. So that means one row, at least one row, will be a linear combination of the others. That means one row will become a row of zeros after certain sequence of elementary row operations, right? So that's what I explained here. So if your A is not invertible, so that the rank of A is less than n, strictly less than n, then you will see a row of zeros after certain row operations. So if you see some row of zeros, then that means your A. So if you see a row of zeros after some row operations, your A is not invertible. Okay. Actually, if you see a row of zeros, then that means the rows are linearly dependent, so that your matrix cannot be invertible. So given this matrix A, if I construct this augmented matrix, and then if I perform elementary row operations to convert the entries corresponding to A to the identity matrix, then whatever you have on the right hand side, that will be, so if you can lead to the identity matrix, then at that point the matrix appearing on the right hand side will be the inverse of A matrix. Okay, so this is the usual way to find the inverse matrix. Okay, so you know how to find this matrix, right? I mean, let me calculate just a few steps. So given this A matrix, okay, what is the starting point? You look at the first row, first column. Okay, in this case, you have 0. So if you have a 0, then you need to consider the interchange operation. So that means you need to interchange the first row with second or third row. So suppose that I exchange it to the first row and the second row, then your matrix becomes 2, 4, 2, and 0, 1, 0. since I'm performing the exchange of the first row and the second row, the first row goes down, so 0, 2, 4, 1, 0, 0. And the third row is unchanged. And then to have 1, let me divide each entry in the first row by 2. So in other words, I want to multiply 1/2 to the first row. Then the matrix becomes 1, 2, 1, 0, 1/2, 0, and 0, 2, 4, 1, 0, 0, 3, 3, 1, 0, 0, 1. And then I perform the replacement. That means I multiply -3 to the first row and then add it to the third row. Now, how do I get this -3? You look at this entry in the first row, first column, and the number I want to eliminate is 3. So the number I want to eliminate goes to the numerator, and the one I'm using, it goes to the denominator. And then you always put negative sign in front. Okay, so that will be the number you want to multiply to the first row, and then you add it to the third row. So if I do this, the first two rows are not changed, but the third row becomes 1 times -3 is -3. So -3 plus 3 will be 0. And then 2 times -3 will be -6. -6 plus 3 will be -3. And 1 times -3 is -3. And if you add 1, you get -2. And then you get 0 and -3/2 and 1. So that you have 1, 0, 0 here. And then what is the next step? You go to the second row, second column, and you change the number to 1. So how can I do that? You can multiply 1/2 to the second row entry. Then the matrix becomes 1, 2, 1, 0, 1/2, 0, 0, 1, 2, 1/2, 0, 0, 0, -3, -2, 0, -3/2, and 1. And then using this 1, you first eliminate the entries below that number. Okay? As I said, we will transform those entries below the diagonal to 0 first. Okay? And then you handle the entries above the diagonal. So you change these numbers to 0. And then you change these numbers to 0. Oh, actually, and then you can change the diagonal entries to 1. So using this 1, I want to eliminate this -3 in the third row. So the number I want to eliminate is -3. The number I'm using is 1. And then if you put negative sign in front, then you get the value 3. So that means you multiply the number 3 to the second row and then add it to the third row. So if I do that, you get 1, 2, 1, 0, 1/2, 0, 0, 1, 2, 1/2, 0, 0, and 0, and 0, and 2 times 3 is 6, minus 2 is 4, and then 3/2, minus the 3 half, and 1. Okay, and then I want to change this number to 1, so I want to multiply 1/4 to the third row. Then the matrix becomes 1 2 1 0 1 half 0 0 1 2 1 half 0 0 0 0 1 and 3/8 and negative 3/8 and a quarter. Now, so below the diagonal, I have zeros. Now you can change these numbers above the diagonal to 0. How do I do that? First of all, if you multiply negative 1 to the third row and then add it to the first row, then this one will become 0. And then when you multiply negative 2 to the third row and then add it to the second row, this 2 will become 0. So in this way, you can eliminate 1 and 2 in the third column. And then you multiply negative 2 to the second row and then add it to the first row, then this 2 will become 0. Okay, and when you do that, the entries in the first and second rows will be changed. And probably you get a matrix like this. So that's how we obtain the inverse matrix. Okay. So given A, if of course if A is invertible. So if A is invertible, then given A, I can construct this huge augmented matrix, and then you perform row operations as I showed. Then your A, if A is invertible, then A will become the identity matrix. Then the identity matrix in C will become certain matrix, and that matrix will be your inverse. Now, given this A, if I perform the same operation, then given this augmented matrix, if I perform the row operations at some point, some row of A will become a row of zeros. So that means, or a row of zeros. So that means the matrix on the left, for this matrix, the rank will be less than 3. So that means the rank is less than 3. Then, and this matrix is obtained from the matrix above or the matrix on the left by performing some row operations. And row operations do not alter the rank, right? The rank is preserved. So that means my original matrix has rank less than 3. That means this matrix is not invertible. Example 7 is quite interesting and it might be useful in some applications. So please listen carefully regarding example 7. So suppose that we have a mapping T from P2 to P2 defined by this. Okay. So here f prime denotes the first derivative and f double prime represents the second derivative of f. Okay. Then given the standard ordered basis of a P2 space, that means this beta consists of 1 x and x squared. We can find the matrix representing t with respect to p, right? Now, how do I find this? You need to find the image of the vectors in a basis. And this beta consists of 1 x squared. So what is the image of 1? Image of 1 is 1 plus the derivative of 1 plus the second derivative of 1. The first and the second derivative of 1 are just zeros, so it is 1. And t of x will be x plus the derivative of x plus the second derivative of x. The first derivative of x is 1 and the second derivative of x is 0. So you get x plus 1. And the image of x squared will be x squared plus the first derivative of x squared and the second derivative of x squared. So that is x squared plus 2x plus 2. Now, if I write down this 1 as a linear combination of the vectors in beta, this 1 is 1 times 1 plus 0 times x plus 0 times x squared. X plus 1 is 1 times 1 plus 1 times x plus 0 times x squared. And x squared plus 2x plus 2 is 2 times 1 plus 2 times x plus 1 times x squared. So this 1, 0, 0, these coefficients go to the first column of the matrix. And then the coefficient of the next vector, 1, 1, 0, go to the second column. And this 2, 2, 1 go to the third column. So that's how we construct this matrix, right? And the beta is the standard ordered basis. And as the name says, this order matters. So the beta consists of 1x squared, not x squared x and 1. So if I change a basis, the matrix will be changed. So if if I define gamma by x squared x and 1, then the matrix with respect to gamma will be, okay, gamma will be 1, 2, 2, and 0, 1, 1, and 0, 0, 1. So please check this, okay? Please check this one for this gamma. So if I change the order of a basis, or if I change the vectors in a basis, everything will be changed. Anyway, this is the matrix representing t with respect to beta here. Now, given this matrix, if I consider 1, 1, 2, 0, 1, 2, 0, 0, 1, and then if I paste the identity matrix, and then if you perform the elementary row operation, then the matrix on the left will become the identity matrix, and you get the inverse matrix from the right hand side, right? So the inverse of this matrix, so So by doing this row operations, I can find the inverse matrix. Please check this. So this is the inverse of this matrix, and so given this matrix, and this matrix will be, by the some theorem we considered, that will be this inverse is the matrix representing this inverse mapping with respect to beta. Then what is the meaning of this? Its meaning, this one implies that the inverse of some vector, okay, will have the coordinate of this matrix times the coordinate of the vector. So what is this? This is the times the, we used x here, f. This is the coordinate of f of x with respect to beta. Okay. So given this f of x, we can find its inverse image, then its coordinate. So this portion represents the coordinate of this can be found by multiplying this matrix representing T inverse multiplied by the coordinate of f of x. So that will be this. So that means if you want to construct this T inverse of f of x, you can construct a linear combination of the basis vectors using those numbers as the weights. So a naught minus a1 will be the coefficient of 1, and a1 minus 2a2 will be the coefficient of x, and a2 will be the coefficient of x squared. Okay, so in this way I can find the inverse image of any second order polynomial. So this example 7 tells you how to find the inverse image of this T. Okay, T is invertible, right? Because its matrix is an invertible matrix, so that we could find its inverse, right? So that means the T is invertible, and that means for any polynomial, I can find its image, but also given any result of this T mapping, I can find its inverse image. And example 7 shows how to find such inverse image of a polynomial. Excuse me. Okay. Now let's go to section 3. And when I have many equations, then we say we have the system of equations. Given this, so given n unknowns, or they say n the unknowns or n variables. Okay, given this n unknowns, they satisfy m equations, then given this, sometimes mathematicians do not want to write down this and using this system of equations. We want to express it in a simple notation. So instead of writing down this plus or equality sign, we want to describe it using some matrix. So given this system of m equations, if you just extract the coefficients appearing on the left hand side, so if I just take the coefficients of x1 up to xn, then you will get a matrix A. So such A will be called the coefficient matrix. Sometimes I can consider a little bit larger matrix actually, and if I use B to denote the entries on the right hand side, and if I define X to, to define these unknowns, then A times X will be the expressions on the left hand side. So the system of equations can be written as a single equation, AX equals to B. And we have some matrix equation. Okay. And given this B, sometimes we will consider a larger augmented matrix constructed by A and B. So that will be called the augmented matrix, corresponding to, we can consider this augmented matrix. And sometimes we will play with the coefficient matrix. So if the coefficient matrix is m by n, then that means you have n unknowns and m equations. Given this ax equals to b, given this system of m equations in n unknowns, when I say a solution to the system means this, okay? So if some vector s is a solution, then that means s, when plugged in place of x, the equation becomes true. Okay? So I mean a times s will be x. A times s will become b. If that is satisfied, then we say s is a solution. Okay? And when I say the solution set, that is the collection of all the solutions. We say ax equals to b is consistent if there is a solution. Otherwise, we say the system is inconsistent. Okay, so we say ax equals to b is said to be consistent if there is a solution. So if you have at least one solution, then we say the system is consistent. We say the system is inconsistent if there is no solution. So inconsistent means there is no solution. Consistent means it has at least one solution. Okay. Now, A times, so we say S is a solution of AX equals to B if A times S equals to B. But what does A times S represent? What is the meaning of A times S? A times S will be a linear combination of the columns of A matrix using the entries of S as the coefficients, right? So S is a solution of AX equals to B so that A times S becomes B if and only if this B, the vector on the right, is a linear combination of the columns of A matrix. Okay, and of course, that means at that point the coefficients of the linear combination will be the entries of S vector. And AX equals to B is consistent. That means there exists at least one solution. But since A times X is representing a linear combination of the columns in A matrix, so the equality, so it is consistent, means that means B, so it is consistent means that implies that B can be written as a linear combination of the columns of A. So B belongs to the space generated by the columns of A matrix, right? So previously we considered the span of the columns of A, so that will generate certain space, right? So if AX equals to B is consistent, then that means B it belongs to that space. So here, if A is on M by N matrix, then L sub A transformation changes. It is a mapping from Rn to Rm space. I'm sorry. So Fn to Fm space. Then span of the columns in of A matrix will be a subspace. So it will be a space in Fm space. And if B is one of the vectors here in this space, then since definitely AX equals to B will have a solution. But if B is not, B is outside of that space, then that means for any X vector, for any X, if I consider corresponding linear combination of the columns of A matrix, you cannot generate a B vector if B is outside of this space. So when I say AX equals to B is consistent, that means B is in the space, okay, generated by the columns of A matrix. So as an example, yeah, as an example, if I have a point x1, y1, and x2, y2, and suppose that I have some point x3, y3, okay? And as you can see in this data set, there is no line, no mx plus b, mx plus n, which passes through three points, right? So we know that there is no such line passing through these points, right? Now, what does that mean? So if I consider mx1 plus n equals to y1, mx2 plus n equals to y2, mx3 plus n equals to y3. If so, that means so there is no such line. That means when I consider this a system of equations, that is inconsistent, right? So that is the meaning of this. And that means from this left-hand side, if I construct a coefficient matrix, and y1, y2, y3, this b vector cannot be generated, okay, as a linear combination of those two columns of the coefficient matrix, right? So if I call this guy by b, and if I call two columns of the coefficient matrix by a1 and oops, and a2, then if that is inconsistent, that means there are no C1 and C2 such that this B can be written as C1A1 plus C2A2. So there is no such pair of coefficients satisfying this equation. So that means B, when I consider the span of A1 and A2 column vectors, then B does not belong to this space. Okay, right? So in this case, this B is outside of such a space. So there is no line passing through these all 3 points. So that's why in some statistics we rely on regression, right? But anyway, that is one example of situation. So anyway, we say the AX equals to B is consistent. That means B belongs to the space generated by the columns of A matrix. Otherwise, the problem is inconsistent. So being consistent or inconsistent depends on, okay, whether you select your B from this space spanned by the columns of A matrix or not. So here is some example. So consider the following problem. And if I consider this as a matrix times the solution, the unknown vector equals to the right-hand side vector, okay? So in that case, we can also, the system can be written as AX equals to B, okay? And For this problem, for this problem, you can show that there exists only one solution. Okay, you can check. You can check. You can just solve this problem, and you can show that there is only one solution. Right? I mean, there are many ways you can draw the graph of x1 plus x2 equals to 3 and x2 equals to x1 minus 1. Then you can find some intersection and that will give you the solution. Okay, or you can do some algebra and find the solution. So anyway, the point is that for this specific problem, there is a solution and their solution will be unique. And being unique is related with the columns of the coefficient matrix. If these columns are independent, you can check that, you can show that the solution will be unique if it exists. So I will go back to that statement later, okay? So my claim is that since the columns of A are linearly independent, if the solution exists, then it will be unique. Okay? So the solution may not exist, but if okay, even if the columns of A are linearly independent, solution may not exist. I mean, in this specific example, in example 1, we have only 2 by 2 matrix, so we always, I mean, okay, but anyway, in general, so in case of example 1, the situation is very simple, but in general, m by n matrix A, if the columns of that matrix A are linearly independent, then if the solution exists, then it will be unique. In B, we have a problem, and in this case, there are many solutions. And as you can see, the columns of the coefficient matrix are not independent because you have more columns than the number of rows. So the columns are not independent. Do you understand what I am saying? So if you have more columns than rows, then the columns are definitely linearly dependent. And in that case, if a solution exists, then solution you will have many solutions. Sometimes solution may not exist. Well, if you see the graph of those two, there is no intersection, even x1 and x2, 1, 0. So there is no intersection, so there cannot be any solution. There can, okay, so there's no solution. So these three examples show that there are three possibilities for a linear system. There may not be any solution at all. Sometimes you have only one solution, or sometimes you may have many solutions. So there are only three possibilities, okay, for a linear system. So if you find, say, two solutions, then that means you have many solutions, infinitely many solutions. Now, given AX equals to B problem, given if the right-hand side vector B is identically 0, so that means the problem becomes AX equals to 0. Such a problem will be called a homogeneous problem. So we say the system is homogeneous if the right-hand side vector b is 0. If b is a non-zero vector, then we say the system is non-homogeneous. Now, in case of homogeneous system, it always have a solution. It always, right? Because zero vector when multiplied by a matrix will become 0. So a times 0 is 0, right? So if you consider a homogeneous problem, this 0 vector is a solution for any homogeneous problem. So in case of homogeneous problem, it is always consistent, right? So homogeneous system is always consistent. So the situation will be either it has only one solution or it has many solutions. So it has a unique solution. So either a unique solution or many solutions. In case of homogeneous problem. In case of non-homogeneous problem, you may have, as I said, one of three situations. Either it has a unique solution or many solutions or no solution. Now, let ax equals to 0 be a homogeneous system of m linear equations in n unknowns over a certain field f, and let k denote the set of all solutions to the homogeneous problem. Okay? Then K will be the null space of L sub A. Okay? In other words, so that K will be a subspace of Fn, and its dimension will be by the rank nullity or dimensional theorem that n minus rank of L sub A. Okay? So that will be the dimension of K. Okay? But that is trivial because the null space of L sub A, what is the meaning of this? That will be the vector in the domain such that, no, excuse me, the image of, no, excuse me, oh, sorry, image of X under L sub A transformation is 0, but what is the image of L sub A? That is the A times X. So we are looking at the set K. Okay. So theorem 3.8 is a very trivial fact. Now, if m is less than n, then this homogeneous problem has a non-zero solution. Okay. But what does that mean? If m is less than n, so that means you have more columns than the equations. And the number of columns represents the number of unknowns and number of equations. So n is the m is the number of equations and n is the number of unknowns. Number of columns, and that represents the number of unknowns, and m denotes the number of rows, and that represents the number of equations. So if n is greater than m, then that means if there are more unknowns than the number of equations, okay, then so that is the condition, then ax equals to 0 has a non-zero solution because 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 a has linearly dependent columns. If n is greater than m, if you have more columns than rows, then the columns are linearly dependent. Okay. Then ax equals 0 has a non-zero solution. Now, as I said, ax equals 0 always has a zero solution. But if ax equals 0 has additional non-zero solution, then that means ax equals 0 has many solutions. Okay. So let me go back to the example B here. So here in B, you have three unknowns, but only two equations. Then for that matrix, let me temporarily consider the homogeneous problem. Then the claim of this corollary is this: if you have more unknowns, you have three unknowns than two equations, then mathematically this matrix has linearly dependent columns. Linearly dependent columns, then this problem will have infinitely many solutions. Why? Why do I have this research? Because if the number of columns is strictly greater than m, then the rank of A will be the number of linearly independent columns of A matrix. That is the definition of the rank of A. I mean, that was the main property of the rank of a matrix. So this rank of A, or the rank, it is defined by the rank of S of A, but we derived one theorem saying that this rank of A just counts the number of independent columns. And as I said, the rank of a matrix, or the rank of S of A, that is bounded by the number of rows and the number of columns. That was the claim I mentioned at the end of the class, right? If A is an m by m matrix, the rank of A is bounded by the minimum of m and n. So if m is less than n, if m is less than n, then the rank cannot be greater than m. So this rank will be bounded by m. So dimension of this K will be n minus rank of this matrix. So that will be greater than n minus m, and n minus m is positive. Okay, so that means this space has positive dimension. So that K cannot be the zero space. Please remember that dimension of zero space was 0. So there must be a non-zero vector in the space. Anyway, okay. Oh, sorry. It's 46. So let's call it a day here, and let me continue next time. Okay. Thank you for listening, and see you next time.